So this one is example 6. So for the frame shown, calculate the horizontal deflection at the support. All members have a flexural stiffness EI, and we're going to ignore shear deformation. So since we've done this quite a few times, let's just go straight to the calculation. So we've got a UDL on this goalpost, and that's going to be a value W. It's of length L, or span L, so that's WL over 2 for the reaction, and that's going to be WL over 2 for the other reaction. One end is pinned and the other end is on a roller, so you would expect the frame to deflect something like there, so that would be the deflected shape. In the roll system, draw the bending moment diagram. Oops. So let's just forget that. So the bending moment diagram is going to look something like that, and as we had in the previous example, that's going to be WL squared over 8 for the maximum values. Just a quick note, since there's no horizontal force, that value is going to be 0, and so there can be no bending moment in the columns, and if there's no horizontal shear at the column base, then the bending moment up there at the top of the column has to be 0, which is why that value there starts off at 0 and that value there starts off at 0. So let's go on to the virtual system, where we say again there's going to be no deflection. So in the virtual system, we're going to want to work out our real deflection delta in the real case. So let's say that we know that it's going to move in that direction there, so let's stick on our 1 kilonewton bar, and I'll try not to mention the bars again. So therefore that one has to be equal and opposite, so that's also going to be 1 kilonewton in the virtual system, and there's going to be no vertical force, so I'll just show those as 0. Just be precise, 0 kilonewtons. Now the bending moment diagram of that one there, if for example that one had been fixed and that one had 1 kilonewton, you would expect a bending moment diagram, well, you would expect it to deflect round and that to be the tension side, so you would expect a bending moment diagram of something like that, and if that distance was L over 2, then the magnitude of the bending moment would be L over 2 times 1, so that's going to be, that's going to be L over 2. So if that helps us with the bending moment, so that one is going to be L over 2. Same idea on the other side, that value there, the magnitude of that value is also going to be L over 2, so the bending moment can't switch sides, so for the beam it's also going to be L over 2. So that means that that magnitude is going to be L over 2, and that magnitude there is going to be L over 2, and that magnitude on the column is also going to be L over 2. Now, as we saw in the previous examples, let's call that member 1, member 2, member 3, so that would be member 1, member 2 and member 3. We're going to be multiplying the bending moment diagrams. So for the two member ones and for the member 1 in the row system, the bending moment is going to be 0. So it's going to be 0 times the virtual bending moment of member 1, which is also going to be 0. And the same applies to member 3 or the column 3 in the real system, the bending moment on that column is going to be 0. So even though the virtual system has a bending moment, it's going to be 0 times something, which is going to be 0. So we only need to concentrate on member 3. So, sorry, I need to concentrate on member 2. So delta for the horizontal deflection, that's going to be the integral for member 1, which is going to be m bar over EI dx, and that's, well, from 0 to h over 2, but we know that since that m is going to be 0, that the whole thing can cancel each other out. For the beam, m, I'll just be precise and put mx, m as a function of x, m as a function of x bar, so that one should have been m as a function of x and m as a function of x bar. Divide by EI, and so the integral is going to go from 0 to L, so that one has to be solved, and then the last one, we could just have it 0 to h over 2 or h over 2 to 0, whatever you wanted. Mx times mx bar over EI dx, and since we know that mx for that member is going to be 0, that's going to be 0, then the whole thing becomes 0. So the horizontal deflection is just going to be our delta. Let's just remove horizontal deflection as it gets confusing. So our delta is going to be equal to the integral from 0 to L of the real bending moment times the virtual bending moment, dx over EI. So let's take the EI's out, and then let's use our theorem, which was given to us in appendix, given to us in appendix 2 again. I seem to have lost. So the result of the integral mx times m bar x dx is going to be the area of that, where that is length L, and then that is WL squared over 8. So it's going to be the area of that multiplied by the value on the virtual bending moment diagram taken at the centroid of that parabola, which is going to be there. So we know that that one there is just going to be constant, since the bending moment is constant over the length as L over 2. So as we showed up there, that L over 2 has been constant, so we don't even need to worry about the value at the centroid of the parabola. It's going to be L over 2 constantly. So we know it's a parabola. Then again from appendix 2, I'll try and get this right first time here. So that's going to be the area, which is obviously going to be of half of what we've just drawn up there. So that's going to be the length times the height times n, which is going to be 2, divided by m plus 1, which is going to be 3. And then the length is L over 2. And then the height is WL squared over 8. And obviously that's just represents half of that, so it could be either half, so it just represents half of that. So the total area is going to be equal to 1 over EI times 2, because there's going to be 2 of those. That's going to be multiplied by the length, which is L over 2, times the height, which is going to be WL squared over 8. Multiply that by L over 2, and that, I've lost the 3 again, haven't I? It's going to be length times WL squared over 8 times 2 over 3, well, that 2 comes from there and the 3 comes from there, multiplied by L over 2. And cancel those out, cancel those out. And we are going to get WL to the 4th, because we've got 1 L there, 2 L's there, and another L there. Divided by EI, multiplied by 8 times 3, which is 24. So that tells us that that deflection there, which we've just calculated, is going to be equal to W L to the 4 over EI. Well, just put 24 EI. And of course, that ignores shear deformation. And it also ignores axial deformation, which would be the n times n bars. No, just ignores the shear deformation.